Let us verify Green's theorem for the integral of minus y dx plus x dy, and that integral is along a curve given by xt comma yt equal to cos t comma sin t, and t is changing from 0 to 2 pi. Observe that cos square t plus sin square t equal to 1, etc., etc. And so as our t changes, your point cos t comma sin t will lie on a circle. As the point cos t comma sin t will lie on a circle, and as your t changes from 0 to 2 pi, we get a closed curve. So we want to verify Green's theorem along a closed curve that's absolutely a circle. So we have drawn a circle here that has to be of radius 1 unit, and your t will change from t equal to 0. You will start from that and you will take a complete turn and t equal to 2 pi. So as theta changes from 0 to 360 degree, we get a closed curve. And of course, for Green's theorem, we need the curve to be a closed curve. And then let's write the formula corresponding to Green's theorem. We know that if you want to verify Green's theorem, we are supposed to verify this formula: integral of f1 dx plus f2 dy, integral of f1 dx plus f2 dy equal to integral, that's the integral over a closed curve, f1 dx plus f2 dy, and that is equal to integral over region del f2 del x minus del f1 del y dx dy, dx dy or dy dx, that will depend on which one you are integrating first. Are you integrating with respect to x first or with respect to y first? Now let's compare this with the given question, integral over minus y dx plus x dy, that is given to us. We want to verify Green's theorem and we are given minus y dx plus x dy. Observe that in Green's theorem we have f1 dx plus f2 dy, and your equation you have integral of minus y dx plus x dy. So what should be our f1 and f2? Precisely, f1 should be minus y, f2 should be exactly equal to x. Once again, f1 should be minus y and f2 should be exactly equal to x, and let's put those things in your formula. So we have f1 equal to minus y and f2 equal to x. Then we can write the above formula as integral over closed curve minus y dx plus x dy. So we have taken f1 equal to minus y, f2 equal to x. So right hand side will be equal to del f2 del x minus del f1 del y dx dy. So let's compute del f2 del x minus del f1 del y. Once again, first of all, we have f1 equal to minus y and f2 equal to x. So f1 equal to minus y, f2 equal to x. Then del f2 del x minus del f1 del y. That's the thing that we need to integrate on the Green's theorem on the right hand side. That is equal to del x of x minus del y of minus y, and that is equal to del x of x is 1 and del of minus y is minus 1, so that is just equal to 2, equal to 2. So what will be our left hand integral and right hand integral? Let's compute it. Left hand side and right hand side. First of all, we want to verify Green's theorem, and for that we have f1 equal to minus y and f2 equal to x. And we have observed that del f2 del x minus del f1 del y, this is just equal to 2. So double integral over a region del f2 del x minus del f2 del x minus del f1 del y dx dy is just equal to 2 into double integral over region 2 into dx dy. However, if we look at the region, that is just a circle. The region is just a circle that is of radius 1 unit. So if you integrate dx dy over this region, you'll get the area of the circle. You'll get the area of the circle, and that is equal to pi, because radius is 1 unit. So we have computed right hand side equal to 2 pi. Now let's look at the left hand side of the Green's theorem. We have got minus y dx plus x dy. In the left hand side we have got minus y dx plus x dy, and that is given in the question as well. So let's compute the left hand side of the Green's theorem. Integral minus y dx plus x dy. However, we are also given that the curve that we are integrating is y equal to sine t and x equal to cos t. That makes our work much easier in this case, in fact. We are given y equal to sine t, x equal to cos t, and t is changing from 0 to 2 pi. T is changing from 0 to 2 pi. T is greater than or equal to 0, less than or equal to 2 pi. So can you compute this integral? Yes, we can compute it. Your t is changing from, let's write everything in terms of t. That makes it much easier. T is changing from 0 to 2 pi. Y is your sine t, so minus sine t dx. X is your cos t, so dx is derivative of cos t is minus sine t dt. What about the other integral x dy plus integral 0 to 2 pi x dy. X is just cos t and its y is sine t, dy is d of sine t is cos t dt. Now integral we can add it, and this we can write it as, we can simplify it, it's 0 to 2 pi. Minus minus, we can write it as plus, minus into minus is plus, sine is square plus cos is square is 1. Wow, that is just equal to 2 pi. So we got the same answer in both the cases. So we have verified Green's theorem. We got the double integral over the region that was equal to 2 pi, and now if you integrate over that curve, over that boundary, again we get 2 pi. Thank you.